Hi everyone, I'm going to start 10.8, torque and angular acceleration. So we know that a torque acting on an object causes that object to rotate. So that means that it causes an angular acceleration. And let's look at how to find this. So if we consider again a rigid body that's made up of many particles with mass, we can write each mass element as having a mass mi, which is at a distance ri from the axis of rotation, and is experiencing a force of Fi. So it would look something like this. And just for this example, I've chosen forces that would rotate the object counterclockwise. So in this case, and for many irregular shaped objects, often the tangential component of the force method works best in order to calculate torque. So let's look at doing that. If I write the tangential component of the force on acting on each mass element, we have mi times that tangential acceleration, since the net tangential force will cause a net acceleration in the tangential direction. Okay, so then using this method, we have torque equals Ri times F tangential, and I showed why that works in the last module. And then we can plug in for F. So we have Mi times A for that tangential force, and it's the tangential acceleration. So if you go back to the beginning of this module, we also said that the tangential acceleration is equal to alpha r. I've labeled this alpha z because I've drawn, again, this shape that's rotating in the xy plane. And if the object is rotating in the xy plane, then its angular acceleration will be in that z direction. So that's alpha z here, ri. Okay, so now just plugging that in and rearranging, we have mi ri squared alpha z. And you might notice that that quantity looks familiar, this first one that I've underlined. That is the moment of inertia for this particular mass element there. So that's its moment of inertia, I, mi ri squared. And so then what we have is the torque on that mass element is the moment of inertia of the mass times alpha, the angular acceleration. And this object will rotate with at one time where all mass elements have the same angular acceleration. So we don't need a subscript on alpha. Okay, so to find the net torque, we're always going to sum the net torque acting on all objects in the system, in this case, all elements of the mass. And when we do that, we have mi ri squared alpha, and then we would sum them as to as many mass elements, in this case, nearly infinite. And then what we can do is pull alpha out of that sum since it is constant. And then look, this first part, the sum of all mi ri squared, we know that that's just the expression for the total moment of inertia. So we have our net torque, which is along the z-axis as well for this rotation in the xy plane, equals I, the moment of inertia of the object, times alpha. So this is really equivalent to Newton's second law for rotation. Instead of having our net force equals mass times the linear acceleration, we have our net torque equals the moment of inertia times the angular acceleration. So we'll look at calculating some net torques and angular accelerations for objects, but I just want to talk briefly about the angular acceleration due to gravity. Okay, so we've calculated gravitational torque before, but now that we're talking about a rigid body, just remember that the force of gravity acts on every element of mass within that rigid body. However, we can treat as long as the gravitational field is uniform, which it is for objects near the surface of Earth, then we can treat the force of gravity as if it acts on the center of mass only. And that's not an approximation as long as the gravitational field is uniform. So to calculate the net gravitational torque, we'll take the position of the center of mass, r, cross Fg, the force of gravity. And then we can calculate the torque due to gravity, which can contribute to the angular acceleration. So just two more things before we do an example about torque and angular acceleration. First of all, the net torque is caused by the net external forces acting on the objects. So if we calculate all the torques by all of the external forces and add them up, then we get the net torque. So all of the internal forces, due to Newton's third law, would cancel, so they would not cause any net torque. And now, as I mentioned, these quantities have analogous quantities in our translational physics. So we have the net torque analogous to the net force, moment of inertia analogous to mass, and then alpha, the angular acceleration, which is analogous to the linear acceleration. Okay, let's look at the first example. The moon exerts a net torque on the Earth of 2.67 times 10 to the 17 Newton meters through tidal forces directed opposite to the direction of Earth's angular velocity. Calculate the resulting angular acceleration. Okay, if you remember previously, I did say that the accepted moment of inertia for the Earth is 8 times 10 to the 37 kilograms meters squared. That's really all we need, and then we can use just the simple relationship that the net torque equals I times the angular acceleration. So we solve for alpha, net torque over I, so 2.67 times 10 to the 17 Newton meters over 8 times 10 to the 37 kilograms meters squared, which gives 3.3 times 10 to the negative 21 radians per second squared. You can look this up actually, it's fairly accurate. The moon does cause these tidal forces that have an effect on the angular acceleration of the Earth. And actually due to this, the length of a day would increase by 10 milliseconds every 100 years. So a small effect, but it's there. Okay, next example. A uniform rod of length L and mass M is attached at one end to a frictionless pivot and is free to rotate in the vertical plane. A, what is the initial angular acceleration of the rod and translational acceleration of its far tip? What is the acceleration at the instant the rod has swung through 90 degrees? Okay, so in this question, we're looking at a thin rod that's rotated about one end. So let's go to our table and then look up that value. Well, we've used this one a few times, so that's 1/3 ml squared for the moment of inertia of the rod. Now, in this horizontal position, we know that the force of gravity is acting at the center of mass, so we can put that there, or we can treat it as it's acting at the center of mass. And then we don't know the forces that are acting at the pivot here, but we don't need them since they won't cause a torque on the object. They're at a position of r equals 0. So any forces applied at the pivot cause 0 torque. Force of gravity will cause a clockwise rotation, so it will have a negative torque. What we want to do here is calculate the torque due to gravity and set it equal to I alpha so that we can solve for the angular acceleration. Okay, so looking at torque for a constant force, we have negative mg, this is F, r, sine theta. So negative mg, L over 2, sine of theta. And in this first position, it's sine of 90, which is 1. So we just have negative mg, L over 2. Now I'm going to equate that to I alpha. So moment of inertia, 1/3 ml squared alpha equals that torque we just found, negative mg, L over 2. And if you look, we have the factor of m canceling, one factor of L, and solving for alpha, the 3 multiplies up, and we have negative 3g over 2L for that angular acceleration. So that's clockwise as well, in the same direction as the net torque. Okay, so now calculating the tangential acceleration at the end of the rod at this point, we have r alpha for tangential acceleration, which is L, distance to that center of the rod from the pivot point, to the end of the rod from the pivot point. So L times 3g over 2L. From alpha, plugging that in, L cancels, and the tangential acceleration at that point is 3g over 2. And we wouldn't say positive or negative for that necessarily, since it is a linear quantity, and generally we would use a coordinate system to describe that. So it's okay to leave it like that, or maybe to say down at that point. All right, so now for B, it's asking us, now the thin rod has rotated so that it's in this vertical position here through a 90-degree rotation. And what is the angular acceleration and the tangential acceleration now at that point? Okay, so I've erased everything so we can try part B. Now when the force of gravity is acting here, that's going to be parallel to the position vector r from this pivot there. So since it's parallel along that vector, we have sine of 0. So that will give us a net torque of 0. We still would have mgl over 2, but since it's times 0, it doesn't really matter anyway. And then the net torque is 0, which means that alpha is 0. And when we go to find the tangential acceleration, it's actually 0 as well. So after falling to that point, it would not continue to accelerate. Okay, one more example. Sample 17, a block of mass m1 equals 2 kilograms and m2 equals 6 kilograms are connected by a massless string over a frictionless pulley in the shape of a solid disk with radius r equals 0.250 meters and mass m equals 10 kilograms. The ramp on which one block rests is frictionless and has an angle of 30 degrees. Determine the acceleration of the blocks and the tension in the string. Okay, so I'm going to go through each mass in the system separately, and we'll write out the net force or the net torque on that object. So this problem we've seen before, but before we used an approximation that the pulley was massless. In this case, we're going to account for the mass of the pulley, and that means that we need to account for the torque that the tensions cause on the pulley, and this causes the tension in either side of the string, on either side of the pulley, to be different. So it will cause a difference there, and we can no longer assume that the tension in the string is the same everywhere if the pulley has mass. Okay, so first thing to consider is that as the objects move, they'd be over on these two sides of the pulley. If the string doesn't slip, then the string has to move with those objects. So the tangential velocity of the pulley, the speed of this outer rim, would have to be equal to the speeds of the masses at any point. And that's equal to omega r, so we can use that a bit later. Secondly is that the acceleration for the system, the acceleration of those two masses, they're still connected, so they'll accelerate at the same rate, and that acceleration will be the same as the string and thus the outer edge of the pulley. So that's what I've written here. A masses is the acceleration of the rim. That's the tangential acceleration, so that equals r times alpha, the angular acceleration. All right, so when we look at this pulley, it's a uniform disk, so we can find the moment of inertia. It's 1/2 mr squared. And then write out the net torque on this pulley. So for the net torque, we have both forces here acting at the radius, so a distance of r from that center pivot point. And then we also have the forces in different directions. Now, before we were using the sign as clockwise is negative, counterclockwise is positive. I'm going to change that system here because if you remember, for connected objects, we want them all to accelerate in the same direction. And the direction that the system accelerates in, we choose that to be the positive direction. So in this case, it's accelerating this way because the heavier mass was on the inclined portion of the problem, portion of the setup. So this rotation this way, which is actually clockwise, is going to be the positive direction here. Okay, so the net torque, we have r ft2, which would cause a positive torque here. And then distance from the pivot up to this one is still r ft1, but negative, of course, now it's in the negative direction. So r ft2 minus r ft1 equals I alpha. That's our definition for net torque, just on the pulley here. Then I can plug in that moment of inertia, so we'll have r ft2 minus ft1 is 1/2 mr squared alpha. And just to simplify for now, ft2 minus ft1 equals 1/2 mr alpha. Now we're going to have three unknowns. Unlike before, when we solved this, we would have only had two unknowns, the tension and the acceleration. We can either solve for linear acceleration or angular acceleration, since we can plug in for one or the other. So in this case, our unknowns are ft2, ft1, and that angular acceleration alpha. So we'll need three equations, and they come from analyzing each object in the system. So that's equation 1. Okay, I'm going to erase, and then we'll look at the masses. Okay, so now analyzing these two masses is review. We've done this many times. So for mass 1, it's on the flat surface. Its positive direction is horizontal, which is towards the direction of motion for the system. So we just have Ft in that direction. Fn and Fg are in the other perpendicular direction and are balanced anyway. So we get Ft1 equals m1a for the equation for that mass. And that's our second equation. I'll call it number 2. And now looking at the incline, again, very familiar, we can write the net force on the incline. We need to use this x direction down the incline as positive to match the overall positive direction of motion for our connected system. If you solve another way, you'll just have to be careful with substituting the signs. All right, so we have our net force, m2a, m2g sine theta, minus ft2, which opposes that gravitational force. So solving for Ft2, we get Ft2 equals m2g sine theta minus m2a. And so now, if you remember, we had for the torque on our pulley, Ft2 minus Ft1. So we can take each of these relationships for the tension and plug them in there and then solve for the acceleration. So this is really the important theory, and then the rest is just substitution and algebra. But I'll show you how to do that now. Okay, so we started with equation 1. This one, Ft2 minus Ft1 equals 1/2 mr alpha. Now, equation 3 and 2 were in terms of a instead of alpha, so let's plug in for a, the linear acceleration here, especially since that's what we're solving for the masses. A is r alpha, so it's really easy. We can just replace r and alpha by a. There, okay. And then plug in equations 2 and 3 from the previous board. So 3 was, for Ft2 was m2g sine theta minus m2a, and then Ft1 was m1a. So we have minus m1a, and that equals 1/2 m, capital M for the mass of the pulley, times the acceleration. Then just some algebra here, negative m1a minus m2a minus 1/2 m a. So getting those all on one side equals negative m2g sine theta. And then we can just factor out those mass factors and divide by that. So we have 6 times 9.8 sine 30 over 6 kilograms plus 2 plus 5 kilograms, or 1/2 of 10. And then that gives a linear acceleration of the masses of 2.26 meters per second squared. Now that's really the difficult part, I guess. Now we have to go back and solve for the tensions. We're asked for the tension in either side of the string. So we have m1a here. This, we can just do it here since we have the expressions. Ft1 is going to be m1a, and mass 1 was, let's see, 2 kilograms times 2.26. And to get that tension, that gives me 4.52 newtons. And then I can plug back into my expression for Ft2, which is this one here, this bracket. So Ft2 is going to be 6 kilograms times 9.8 sine 30 minus 6 kilograms times 2.26. And then we should find the tension on that side of the string to be 15.8 newtons. So this massive pulley does cause a significant difference in the tension on either side of the string. If the mass of the pulley is small, on the other hand, then it can be a good approximation, if it's a very light pulley, that the tensions on either side would be the same, since that's really what we see that the relationship depends on. So for a small mass, that could be essentially a good approximation, but to be more accurate, we need to account for the torque on the pulley due to those tensions, which causes the difference between them. Okay, next we're looking at work and power in rotational motion. So let me know if you have any questions.